Hey, I'm Kirsch, electrical and electronics design engineer, ex-Intel, and former adjunct professor in electrical electronics engineering. In this video, we're looking at the leakage inductance problem in flyback converters and how to fix it with a snubber circuit. So let's explore how this all works. The controller looks at the output voltage, right? And then it's going to keep the switch on, this MOSFET circuit, on so that it conducts current through the primary side of the transformer for a certain amount of time, or it's going to close it off depending on how much voltage is being seen on the output. When this is turned on, it has current coming through that transformer primary side, expanding that magnetic field. That magnetic field couples with the secondary inductor, all fine and good. When the switch is turned off, that magnetic field dumps energy into that secondary inductor, and that primary current is dropping really fast while this energy is getting dumped into the secondary side. So now that's good operation. There's one problem though. The leakage energy doesn't really have anywhere to go on this circuit. Like there's the leakage between those two coupled inductors. And so you're going to get those voltage spikes like I talked about. So the voltage spike is going to be dependent on your changing current. So your DI, DT, you're changing current with respect to time and any of that leakage inductance. And then that'll give you your voltage spike. If you have something, say, as small as what I said, 0.78 microhenry for your leakage inductance, which doesn't seem like much, but you multiply that by 3 amps over the course of 30 nanoseconds or 20 nanoseconds, you're going to get 117 volts on the primary side. That's a problem. So now your drain voltage over here is going to spike to 50 to 60 volts when it really should only be 18. You'll also get pretty violent ringing when the switch is turned off. You'll even see negative current spikes across that MOSFET. Now, with all of these issues, you figure this would be relatively okay as long as the flyback works, but there's one problem. It's the EMI. Those power supplies, if they're not built correctly, then you're going to get a lot of EMI and you're going to fail emissions testing. This has happened to me numerous times, and especially on one big project with my team of mine, and we just couldn't pass the EMI testing for a good 2 to 3 months. And it came down to that power supply and a couple of other things. All right. So we want a way to get rid of those spikes. But before I do that, let me show you what this looks like in simulation. This is what the simulation results look like before adding a snubber circuit and making some tweaks here and there. So these are the kinds of problems you're going to get. We have not enough input voltage. Don't worry about that. That gets boosted later. But see this here. This current is going negative. We should not be having this issue. Okay. So it's operating as expected, but there's a little bit of negative dip in there. Here we've got, overlap in terms of the switching, some spiking going on here, way above what we would expect or would hope for, and some ringing intermittently as well. Okay, so this is a problem when you have that leakage inductance in your flyback transformer, which is in every transformer, which is why you're going to need that snubber circuit. Okay, so let me show you what happens once you add a circuit that will help fix this problem. So here's what the snubber circuit looks like. So we've got that leakage inductance happening, right? And it's showing up across this MOSFET, this drain here. What I need is some way to get that negative current. So that's the current that's going upward, okay? Not downward like it's supposed to be, but it's going upward. This needs to go somewhere, not the primary or whatnot. So I need a diode, okay? And a diode. This is part of the RCD, what we call the RCD snubber circuit model. Okay, so I need a diode that will direct that leakage current some direction into V in. Now, when I'm doing that, I also need to have a resistor that can dissipate that current as it goes through my circuit. Okay, so it slows that down, dissipates those moving electrons as heat, and also a capacitor for when I have this voltage that comes as a result of running that current through that resistor, capacitor that smooth out that voltage as well, so we don't have our crazy spikes, okay? With the slowing down of that changing voltage, we have significantly less EMI. So the Snubber circuit does a lot of heavy lifting just because of this leakage inductance in the transformer, okay? Now there are equations to calculate what these values are. They are very particular and persnickety and depend on your leakage inductance. Those equations will be in our design guide or whatever links that are provided around this video. For my calculations, I set the Snubber circuit to have a resistance of 1.5 kilo ohms and a capacitance of 2.2 nanofarads. And I use an ideal D-break diode. You use your appropriate diode that has whatever works for your equations. Okay, so now that I've explained the problem with the leakage inductance in the flyback transformer and how the Snubber circuit fixes this problem for us theoretically, let's see what the actual results are once we run the simulation again. Voila. Now I spared you the run details and everything since it takes a little while, and this is what our output looks like. Let me zoom in on the area. Before I do that, let me show you. So we have our voltage across that drain of that FET still up there, but no crazy negative spikes. We have the current through that MOSFET. The current is looking a little, interesting, but once I zoom in, you'll see what I'm talking about. And then here we have the output voltage steadying it around the 5 volts that it's supposed to be at. So if I were to zoom in on my measurements, okay, there's still some ringing, but look at the performance and behavior. It's more smooth. Now, if you want this to be smoother, you do need to adjust the resistor value, the capacitor value, and maybe leave even a little bit of the diode. But we have less ringing, we have better behavior, okay, more consistent as far as the voltage. To reduce the spikes though, I would change some of these values, but it's looking pretty good, much more well behaved. Now let's go ahead and play with some of these values. Let's say I want to reduce my Snubber resistance down to say 500 ohms instead of 1.5 kilo ohms, right? What's that going to do? We rerun the simulation. Okay, so here are our results. So here we've got the Snubber circuit with the resistor at only 500 ohms. We get less ringing, so that's good, and a little better behavior on the circuit here. So it just depends. If I change my capacitor to say 5 nanofarads and I reduce my, well, actually, we'll just change the capacitor and see what happens. All right, now that I've changed my Snubber resistor value to 500 ohms and my capacitance, I bumped it up to say 5 nanofarads, then the waveforms look cleaner, okay? There are other things you can do to change these, but those are what you could tweak. Now, here's the issue. If you reduce your resistor on the Snubber circuit too much, like if the value is too small, you're gonna get higher power consumption because the clamping voltage squared over the resistor is going to give you more power consumption. Okay, so you got to be careful about that. We don't want to go too low on that resistor. If you make the resistor too large, something like 10 kilo ohms or something, then your capacitor may not have the time it needs to discharge between switching cycles. And you're going to get this clamping voltage. It's going to increase. It's going to get even bigger if the resistor is too big. You're also going to get more ringing the larger resistor you use. Now, when it comes to the capacitor, let's say you make the capacitor too small, something ridiculously small like 100 picofarads. Well, if the capacitor is too small, it can't absorb that energy that's going through that circuit. And the spikes that are in the circuit will break through that capacitor. And then of course, if you don't have a diode on here, you cannot control that current that's coming off of that, the consequence of that leakage inductance. Matter of fact, without controlling that, you're going to see weird phase shift behavior in circuit operation. And if you have phase shifting in your control loop, then you might be misfiring or firing at the wrong time, threatening to blow up the controller and the flyback. All right, so that's a lot of information. I'm just going to do a quick checklist for you. Here we want to check that the leakage from the transformer is you find that in the data sheet, and it's going to be about 3 to 5% of your primary side of that transformer. Okay. And then number 2, you want to know the peak current and the frequency, the switching frequency from your design. So that will depend on the controller you're using and what frequency you choose. Then step number 3, you would pick the clamping voltage or V clamp and leave 20% margin below your MOSFET rating. Meaning if your MOSFET is rated for say 100 volts, right? Plan for say 80 volts and then reduce that by 20% to get to about 56 volts max or whatnot. Okay, because we don't want to be at max and we don't want to be at operational. We want to be 20% under operational and definitely below max. Okay, step number 4, the resistor calculation will be 2 times the clamping voltage that we just got and decided on in a previous step times that leakage inductance, the peak current that you'll be expecting from that, and also your switching frequency, right? Then step number 5 will be the capacitance. What's the calculated number for that? It's going to be anywhere from 1 to 10 nanofarad in general, and that's going to be about the switching period, okay? And then 6 is to simulate, like I've shown you in this video, before building your design. All right, I've covered what I wanted to in this video, that transformer and that snubber circuit, why we use it and what it affects in your design. Okay, the snubber is a trade-off circuit. So you're trading off between efficiency for reliability. You want to size it just enough to protect your switch, but not any tighter than that. And the most important thing, please, 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 is to simulate your circuit first and then validate it on the bench. This is Kirsch bringing you another electronics video, and I will see you in the next one. Peace.